I would like to present our next speaker, who's already ready and hums his hips, Dr. Christian Nietner. He is Head of Quantum Computing and Advanced Analytics at NTT Data and has a PhD in quantum physics. You're responsible for the technological and strategic portfolio development of NTT Data's quantum computing services, and your talk is titled The Configuration Optimization of Pre-Production Vehicles. And this is a report on a working setup which involves a team of researchers from 1QBit, NTT Data, NTT Research, and the University of Notre Dame, and some experts of BMW. Thanks for joining us here. Stage is yours for the next minutes.
Thanks for having me. Excuse me, that's the remote?
That should be working.
Okay. Ah, yeah, brilliant. Okay, well then, thanks for having me, and thanks for having the opportunity to today have 20 minutes to tell you about an industry use case that we jointly tackled and successfully so within the framework of the BMW Quantum Challenge. And basically, what BMW did was phrase this challenge with 4 different use cases from their industry, and we were one of the teams that applied to solve one of these questions. And who are we? Well, we are a team. We built a team for that, consisting, as just mentioned, consisting of 1QBit, a quantum startup based in Canada, the University of Notre Dame, our research colleagues from the NTT Research. So the NTT has its own physical basic research laboratories around the world. There's one in Japan and one in the US. So these colleagues were part of this project, and as well was the NTT Data, which is primarily a system integrator, but has also built up in recent years capabilities in quantum computing. And together we applied for an optimization problem that was posed within this challenge. And to give you an idea of what this was about, basically the problem that the industry, and specifically here BMW, is facing is to test vehicles, right? If you build a new car, a new kind of product, then of course there are regulations and requirements that these products need to fulfill. And for that, there is the necessity to build some prototypes, to perform the tests in order to get the product basically to have it market ready. And the challenge here is, of course, these prototypes were just developed for the tests, for performing these tests, and you want to reduce, of course, the costs. You want to reduce the number of vehicles that you need in order to fulfill all the requirements and tests. So basically, this is the optimization task we were facing, trying to make sure all the necessary tests are fulfilled by the new products, by using the minimal amount of vehicles to basically do so. Because each of them is, of course, expensive to build, and potentially you can't probably sell them afterwards, so they might get destroyed in the process of testing. So basically this was the requirement. And to give you an idea why this is a challenging task in the industry, let's have a look at what are the requirements, what are the constraints within this problem, actually. And this has basically two sides. On the one hand side, of course, we have vehicles that are built, and these vehicles are obviously built, of course, under constraint, right? I mean, there is different types of vehicles. Each vehicle can come with different features that can be accommodated within this vehicle. And there is a lot of them, as you might know if you configured a new car lately. And of course, there are some build constraints, right? If I want to have a certain configuration of a car, then some components need to be included, but some need to be excluded, right? I mean, this, for example, in case here, for the motor block, for example, there might be a build constraint that says within this product we can just build a 6 or 8 cylinder machine, but not a 4-cylinder machine. Or similar constraints, basically. So that's the vehicle side. That is already complicated to tackle simply because there is a huge combination of these possible components, features, models that lead to a huge variety of different possible buildable cars and vehicles. And on the other hand, of course, we have tests that need to be fulfilled. In this case, here we were provided with 3 different data sets in increasing complexity that at least give a realistic glimpse at the situation. So it's not entirely the real world scenario, so probably these sets are even more complicated. But for this challenge we were posed with these kind of test sets, including roughly 10,000 different tests that need to be performed. And of course these tests also have restrictions, right? I mean, you of course have here as well some compulsory, so some necessary requirements of components that need to be included in the cars in order to test them, right? You have a certain order within these tests, so some of these tests need to be performed in different stages of the development process, of the building process. So it could be within the facility already, or maybe afterwards. So these are some requirements. Of course, all these tests have some kind of routine, well, as mentioned, within the building process when they need to be applied, and all of them have a time frame and maybe even a location requirement here to be fulfilled. And finally, of course, tests can be performed on multiple vehicles multiple times, or maybe there are tests like crash tests that can only be performed 1 time because then the car is destroyed. So meaning there's also a number of or an amount of tests to be performed, and they are categorized in the sense of, well, for example, cars destroyed afterwards. So this together makes a rather complicated optimization problem with a lot of constraints and requirements that need to be fulfilled. And so we were trying to tackle this solution, and of course, as in every good quantum project, we started by thinking about the conventional ways to solve that. What's actually able, what are we able to do in the classical domain? And of course, the straightforward approach, so to say, let's say the monolithic optimization would simply be to, okay, take all these requirements, build a complex model, and try to solve it with a optimization solver like set or mix set solver to basically solve this whole mess of a huge problem. And of course, you already guessed that that is rather hard to do, as the complexity of these models and problems are just too big to apply this kind of approach meaningfully. So we came up with another idea, which was basically to try to find a better way to classically approach the system by developing a decoupled optimization approach, where we basically try to, in a meaningful way, separate this rather complex problem into more smaller parts that can be more efficiently be solved. So to summarize here, of course, the advantages, disadvantages, as mentioned. So the monolithic approach, of course, it has, of course, advantages, and one of them, and probably the most interesting one, is that optimality can be proven in a sense. So if this is feasible and you solve it, and you can be sure that you have an optimal solution. And you also have, of course, a lot of technologies that you can already use, right? You can make use of classical hardware, state of the art, and you can also use conventional SAT solvers that are well developed. And on the other hand, we have face a lot of disadvantages, which is, of course, the performance calculating this model is not scaling very well with the complexity. It's rather hard to basically to put all these constraints into one model, so the complexity is also an issue, and of course flexibility is also not given in this approach. With our decoupled approach, we choose a rather different idea here. So basically, we try to separate these optimization problem into a process where we first generate some feasible configurations of vehicles, that fulfill a lot of our that are coupled to the tests. So in order that we fulfill more tests, and then we, in the next step, we try to find a schedule for these feasible cars with their tests. This has the advantage of being way more performant, of course. We can solve this problem way more efficiently. However, of course, we're using now here a heuristic approach, so optimality cannot be guaranteed in this process. So there is some uncertainty into this solution. But still, we gain this performance, and we gain also this flexibility in the solution. And in the end, we still can try to improve or make it even at this stage also in a hybrid approach by, for example, using not just conventional set or max set solvers, but use more exotic ones, for example, like a D-Wave or so annealer technology, so coherent Ising machine that the entity is developing. Yeah, so this is the approach that we followed in the first place, and to give you just some idea what we achieved by using this decoupled method is basically that we found a way to efficiently calculate the number of vehicles for the given problem. As you can see here, we indicated the red line is the best solution that we found, which is basically showing you how many vehicles you need to fulfill a given number of tests. Basically, an optimal solution here that we found was around 2,000 vehicles for these roughly 14,000 tests that had to be fulfilled. So this was pretty much the classical approach, trying to really find a solution here that fits better to the problem and circumvents these performance issues in this approach. And of course, the next step was to understand how a quantum approach for this problem might look like. But yeah, that's why we have, of course, this kind of outlook here for the classical method before coming to the quantum one, that we can efficiently solve this problem, given, of course, the drawback of a heuristic approach that we see. However, scalability is great, and so we looked for the quantum solution in the next step to compare that, and here the approach was as follows. So what we implemented here on a simulator was a Dürr-Høyer algorithm with quantum minimum finding. So basically, the idea here was to build up a two-stage process on a quantum machine, where the first stage is basically preparing feasible configurations, car configurations, right? So this is one first step. So roughly the idea is to build, to prepare feasible configurations of cars within this chip, and then try to, in a second stage, use a Grover algorithm to find the minimum set of cars that we need to fulfill all these tests. So that was the approach that we prepared here. Note that in the first stage we have we used a quantum amplitude amplification in order to find the feasible solutions better. That feed into the Grover algorithm to look for the optimal set, right? And the optimal set is then parameterized via this vector y, which is basically selecting the right car configurations that we want to have in our minimum set of cars in the end. And that was the wrong one here. Okay. It might not be a big surprise that the whole complexity of this problem is too huge for a quantum chip. So one of the first questions, of course, was already anticipating that we need a larger computer and probably also an fully error corrected quantum computer. We were looking at the scaling behavior, right? So how is this approach scaling? Meaning how big do we need our our computing devices in the end to basically tackle meaningful instances of this problem. And yeah, what we find is pretty much we had a look algorithmically for the different stages, and then came up with a combined complexity scaling for the whole algorithm. And also you can see in the plots the circuit scaling for the 2 stages on the lower side of the slide, and the upper one is basically the query complexity of the whole algorithm, also separated in these 2 stages. I know it's maybe not visible so good, but the upper plot is is a logarithmic plot in the y-axis. So scaling here is exponential, but more importantly, you see the red and the blue lines are also corresponding to the 2 different stages. And so you can take from that obviously the harder one, basically that is resulting in the bigger bottleneck is the blue line, is the first part of the stage. So preparing the QAA step, preparing the physical configurations is posing the bottleneck in this approach. Having said that about the scaling in general of this approach, let me now show you in the last minutes what kind of results we could achieve. To give you an idea, basically what we did in the end is iteratively training this circuit, and then sampling the energy spectrum that it puts out. And basically this energy spectrum corresponds then to the set of feasible configurations that we have. So this is the way we'd like to tackle that, and you see we get this energy histograms read out from the circuit, and the idea of course is to have a minimum of energy. So we want to have this curve that we get out of our quantum circuits to be most as low in energy as possible. And that this is actually so that the whole algorithm works, and this kind of expectation is also fulfilled. You can see here. So these are two test runs, or this is showing two different approaches. Let's say it's multiple test runs here, but basically on the upper graph, you see the situation for a fixed number of test vehicles per car type. So that's what we fixed in this iteration. And then sampled basically our algorithm, so trained and sampled it. And then what you see, the color code is the number of fixed vehicles per type. And I'm not sure if you can read it, but basically the number is increasing, where the blue curve is the lowest number, and the green curve is the highest number. And what we see is exactly the behavior that we actually expect. So the more freedom there is to basically fit all these constraints, the less the energy becomes, basically in the sense that we see more and more valid configuration popping out in the end of our algorithm, defining a valid minimum set of car configurations. And this is also true for the other approach that we tested, which is basically fixing the number of tests vehicles in total, so not per type, but the total number of cars that you have available to basically fulfill all the tests is fixed. And also here you can see that by increasing the number of cars that you have to fulfill all the tests, the algorithm becomes better and better. And of course, in the end, there is some kind of optimum that we'd like to achieve. But in principle, this works very nicely. However, of course, as we've seen in the scaling behavior, the outlook is rather that we need a lot more qubits, a bigger and more fault-tolerant quantum computer in general. We saw very prominently that we have the biggest bottleneck in this whole approach is really building up these valid car configurations. And as of now, we're currently working more on the classical approach and try to finalize that. And there's also some work ongoing, still analyzing how the quantum algorithm can be improved. So yeah, we're still working on this. It's still ongoing, and we're also trying to bring this to a publication in the end. And yeah, with this, just in time, I'd like to thank you for your attention.
Thank you for your presentation. So, are there some questions from the audience? Now it's the chance. Okay, then I have a question. So you said you save some resources with this project for BMW.
Mhm.
Let's talk about figures and money. If you can say, how much would it save?
I cannot, but luckily we have the colleagues from BMW here in the audience, so if there really is this interest.
So if you're allowed to say, I would be interested.
Pardon?
If they are allowed to say it,
Sure.
we would be interested. How much money would be saved while using this approach?
What's the value of this use case?
Okay, good, all good. So, another question? No? Okay, then. Thank you very much.